Lecture, we're going to talk about how to think about teaching children related to science, technology, engineering, and mathematics. So we'll be talking about what those particular subjects entail for young children, what skills children have in those areas, and how we can best facilitate STEM learning in early childhood classrooms. So before we get started on talking about what STEM consists of, what children's skills are, and how we can facilitate that, I wanted to make sure that we understand why teaching STEM topics or science, technology, engineering, and mathematics, why that's important to make available to young children. So these are actually some quotes from your textbook that I thought were particularly relevant and important to our lecture today. So there are three main reasons that it is important to make sure that children get access to STEM information and opportunities at a very young age, not waiting until they get to elementary school, middle, or high school, but making sure that that's part of education from the very beginning. So let me start with reading the first quote. So the need for an educated workforce. In today's global economy, a large number of jobs require mastery of STEM. However, in international comparisons of mathematics achievement, children in other nations regularly outperform American children. Similarly, fourth grade science achievement in Russia, Kazakhstan, and Poland, as well as 7 other countries, exceeds that of children in the U.S. Although achievement in science and technology is important, understanding mathematics is strongly connected to both of these areas. As a result, more emphasis is needed on children developing a firm foundation in mathematics during the early years of school. So a couple things to break down here. One is that we don't do particularly well in science, technology, engineering, and math when comparing ourselves to other countries. So one of the potential reasons for this is that in the United States, we tend to assume that abilities in a particular area, be that science, technology, engineering, and mathematics, or even things like sports, are innate, that there's something that you're born with, that you're something that you're naturally good at. And we don't believe that those are things that actually require effort and time spent and attention to learning. That is a different attitude than in many other countries. Other countries are much more likely to emphasize the importance of effort in being good at something, whereas we tend to focus on natural ability. And most people are not naturally good at science, technology, engineering, and mathematics. They do require work and they do require effort. So, part of this is just our attitudes about how people learn compared to attitudes in other countries, and also just our inclusion of STEM topics in children's early lives. So we tend to want to wait on STEM until children get older, when really we should be doing that early. The latter part of this quote is really talking about how if you want to best get at helping children to be good at science, technology, and engineering, you really need to do the M. You need to make sure that they have many opportunities to engage with math, because math is the building block of all of those things. And so when we make sure that children have that building block firmly in place, then they're likely to do better in all STEM topics, not just math. So another piece of this is that we know that we are not necessarily creating the educated workforce that we need in the country as a large in comparison to other countries, but we also have gaps among citizens in our country. So one gap, and we'll talk about this towards the end of this lecture, but one gap is between girls and boys. Another gap is between Black boys and other children, and another gap is for middle income versus low income children. So low income children tend to do more poorly at math, have fewer opportunities related to math achievement than do their more advantaged peers. So we need to make sure that we address that, because as noted in the first quote, research now demonstrates that math skills at kindergarten entry are the strongest predictor of later school achievement and executive function. In an analysis of 6 large-scale longitudinal studies in the United States, Great Britain, and Canada, researchers found that early math skills predicted not only later math ability, but also success in reading. So we know that promoting reading skills among young children is vitally important to their academic and long-term success, but what we're finding out is that math is another biggie, and math is really important not just to math, but also, as I mentioned previously, to science, technology, and engineering, and also to reading. So we can't ignore math in the equation, and we can't wait until children get a little bit older before we start introducing math concepts. So later in the lecture, we'll talk about how can we best facilitate math with very young children rather than waiting until they are older. There are 3 types of skills that children need to possess, primarily possess. There are other skills that are also helpful to navigating STEM and making sure that children get what they need to out of STEM activities and opportunities, but there are 3 skills that are directly related to children's success in STEM, and these are cognitive skills, mathematics skills, and science skills. So we're going to talk about what each of these skills are, what skills young children have in those 3 areas, and how we can facilitate children's growth and learning in those various things. So again, this is looking at sort of breaking STEM down, like what are primary skills that you need to be successful in STEM fields, and talking about what those are, what skills children have, and how we can facilitate those things. So those are cognitive skills, mathematics skills, and science skills. So cognition is thinking. So when we talk about cognitive skills or cognition, we're talking about how children think or their thinking skills. So there are 6 primary areas. So this isn't everything, but these are some primary areas of thinking that children need to engage in to fully flesh out their cognitive skills or their cognitive abilities. So we're going to talk about cause and effect and what children are able to do in that area. We're going to talk about problem solving, attention, memory, classification, number skills, and symbolic representation. So we're going to cover all of those things and think about how children are able to perform in those areas and what is our best way to facilitate all of those different aspects of cognition. This chart is from your textbook and is a walkthrough of things that we typically expect children from birth to about age 8 or 9 to be able to do in terms of cognitive skills. This list is related to those aspects of cognition that we were talking about on the previous slide. So it's related to children's representation abilities, their memory abilities, their attention abilities, their number skills abilities, all of those different things. So you can see, and again, I'm not going to read it all or go over every point, but we'll try and kind of walk through it a little bit. So very young babies, they primarily learn through their senses. So they taste things, they touch things, they smell things, they listen to things, and they also learn using their motor skills. So manipulating things, shaking things, waving things, banging things. So when we think about young children, we think about the fact that their senses and their motor skills are their most important tools for learning about the world around them. They are starting to be able to remember people and objects and favorite toys. That's why they have stranger anxiety, because they realize they don't know that person, or separation anxiety because they realize the person they do know has left. They can pay attention, but they have a fairly short attention span. They are starting to learn that they can create cause and effect relationships, that if they do something, then something will happen in turn. So lots of good skills coming in that first 9 months or so. Then when we get to 9 to 18 months, babies are starting to observe and imitate other people around them. They like to do things over and over again. They use trial and error, or I'll try something, see if it works. It doesn't work, I'll try something different. That doesn't work, I'll try something different. That would be trial and error to solve problems. They enjoy playing with objects, and they also are starting to minimally understand symbols. So they might recognize, not read a symbol, but recognize a symbol and know that it has some meaning in their world. At 18 to 36 months, children don't have to use trial and error all the time anymore. They may have some memory previously and be able to think about what they need to do before jumping in to solve a problem. They are getting better hang of cause and effect. So if I do this, then this will likely happen next. They're starting to sort by simple categories, so putting all of the blue things together or putting all of the red things together. Size and shape, something is bigger, something is smaller, something has 3 sides, something has 4 sides. They should be able to do simple puzzles and start engaging in pretend play with objects. So then we have our preschoolers and our early elementary school age children, 3 to 6-year-olds. They are starting to experiment with cause and effect. I know that this happens if I do this, but what happens if I change it up a little bit and do this? Then what's going to happen next? They are starting to be able to plan ahead about their activities, predict what might happen. They love to engage in socio-dramatic play, so pretending with other children. They are getting better at reasoning and sort of walking out the steps of things, but they do seem to be a little bit illogical. So like they give the example of the food goes into your legs and makes them grow. So there's some logic there. It's just not quite the right logic, but they're starting to think about why things happen and expressing some understanding of that. They're getting better at focusing their attention and persisting at tasks and regulating their behaviors and their thoughts and their actions. Our 6 to 9-year-olds, or our elementary school age children, they are able to take the perspectives of someone themselves. They can make accurate predictions about things that might happen in their world. They can categorize, so they can say there's dogs and there's different kinds of dogs, and then think about sort of the hierarchical categories of those kinds of things. So board games and sports games where the rules are important to playing the game. So lots and lots of different skills that increase over time in terms of cognitive development. So next up, let's talk about math and talk about things that are important to children's math abilities. So the National Council on Teaching Mathematics has stated, and you can take a look at their principles and standards on the link on this slide, but the National Council on Teaching Mathematics has established that there are 5 standards that we should be paying attention to. And we should be paying attention to those math standards from the time that children are very, very young. So even when they're infants and toddlers, we should start including conversations and activities and opportunities related to these 5 math standards. And then obviously what we're doing with those standards will get more sophisticated and complicated across time. But there's no need to wait on geometry until children start high school. And there's no need to wait until algebra, until they start middle school. That we should have strands of all of these math standards from early on, and then we build on those and again get more sophisticated and complicated with ideas as we move along across time. So upcoming, we'll talk about some of children's abilities in these areas. So again, I pulled this from your textbook. Your textbook has lots of great information in it. So this shows you the development of children's math skills in those 5 different math standard areas. as they move from age 2 to age 8. So you can see that children at age 2 can do something called subitizing, and that means that you look at something and you can notice how many objects are there. So if there are 3 objects in a pile and you say 2, that's not the right number of objects. If there's 3 objects in the pile, you need to say 3. That is how many are in that set, and that is subitizing. So they can count, but they may still skip numbers. So they might say 1, 2, 3, 5 and skip the 4, but they're starting to learn that element of rote counting. They should be able to count up to 3 objects, which is why they can subitize 1, 2, or 3 objects, and they should have some knowledge of basic shapes. So that would be sort of the geometry end of things. So 3-year-olds, they are starting to know number names. So if they see a written number, they can name it. They should be able to count from 1 to 10. They should also be able to use one-to-one correspondence. So every object I count has its own unique number. So I wouldn't count 5 objects and say that there's 6. That's not one-to-one correspondence. There's more numbers than there are objects. So there has to be a number for each object. They should know relationships that are mathematical, like more than, less than, equivalent to, or equal. They're starting to be able to put together and take apart numbers, which is the beginnings of addition and subtraction. They're just not writing those problems down yet with the plus and minus sign, but knowing that when I put 2 and 2 of something together, that makes 4, and if I take 2 away, now I only have 2 again. So I don't have to write out the formula, but I understand the way. So 4-year-olds, they understand cardinality. So subitizing is looking at something that has 3 and saying 3. But cardinality is understanding that the last number that is said, so if I say 3, when I'm looking at objects, that means that there are that many. That last number that I say is indicative of how many there are in a set. So not just looking and being able to notice how many are in a set, but knowing that the last number said means something. It represents the total number of objects in a set. So they should now not just be able to count 1 to 10, but they should be able to write 1 to 10, count objects accurately up to 10, and maybe even up to 30, solve simple number word problems. So if I had 2 cookies and I got 2 more cookies, how many cookies do I have? They can maybe count backwards. They should be able to do the mental subitizing up to 5, so glancing down and without having to count, go, okay, that's 5 objects. I can tell just by looking at it. And then be able to recognize and describe attributes of 2- and 3-dimensional shapes. So be able to say that triangles have 3 sides, that squares have 4 sides, etc. So our 5-year-olds, they can compare numbers, so understanding more and less and what different numbers mean. Understand addition and subtraction, so understanding not just, oh, I had 2 cookies and I took 2 away and now I only have 2, but really understanding the idea of subtracting and adding as a mathematical concept. Maybe starting to use simple numbers and symbols to be able to represent that. So classifying objects, so being able to put objects in categories that they go in and know what goes with what. And then comparing, creating, and composing shapes. So not just knowing what different shapes look like, but being able to create those. So our 6-year-olds, they should be able to count to 100 from any number. So starting either at 0 or 10 or 25, they should be able to count up to 100. They should be able to use those mathematical equations related to subtraction and addition, so not having to have actual items necessarily, or using actual items in conjunction with a number sentence. They should be able to understand base 10, so understanding that 10 is 10 ones, that 25 is 20 ones and a 5. So being able to understand how numbers go together and sort of what they mean in that kind of breaking them down way. Telling and writing time, so typically on the hour about this age. Our 7-year-olds, they can conserve number, so they know that 5 always means 5. You cannot have, like, you can't add another object in and have it still be 5, and you cannot take an object away and have it be 5. 5 means 5. Only 5 objects, 1-to-1 correspondence. They can skip count forward and backwards, so you can do odds, 1, 3, 5, 7, 9, 9, 7, 5, 3, 1, or count the evens, that would be skip counting. They can represent and solve problems involving addition and subtraction. So again, using those addition and subtraction numbers. They can work with time and money, so they can probably start doing the half hour now and simple counting things. So at least knowing the main coins that we use and how to count those. And then once we get to our 8-year-olds, they are starting to do multiplication and division. So multiplication and division are kind of special cases of subtraction and addition, and now children have enough experience with subtraction and addition that they can start doing multiplication and division. And they should be able to do this up to about 100 and also add in fractions. So that is a lot of skills in a short period of time that children can gain related to math. So just like there are math standards that are important to pay attention to, there are also science standards or science principles that children should have access to, again, from very early in life. We do not need to wait until children are older and give them formal science lessons. We should be doing science in all of these standards or principles early on in children's lives. So we should be doing life science, we should be doing earth and space science, we should be doing physical science, technology, and engineering. So life science would be biology. This would be plants and animals and humans. Earth and space science would be things like the weather, and it would be obviously our solar system. It would also encompass like geology, so rocks and dirt and those kinds of things. That's all earth and space science. Physical science is how things change. So changes in mass, changes in matter. So this would definitely be like in the chemistry and physics kinds of ranges. So that would be magnets and making chemical reactions among different objects. Cooking is part of physical science. So there's a lot of cool stuff related to all of these things that we can do with young children. And I think technology and engineering hopefully are somewhat self-explanatory, but they do also cover all of these in your textbook. In a minute, we'll talk about some scientific skills that we expect to see children display in early childhood. Your textbook didn't have a nice chart for this, but I did want to say before we get to those developmental milestones that we expect to see, that for all young children, it's very important to engage them in the process of scientific inquiry. So scientific inquiry is when you give children the opportunity to observe and study and experiment with the world around them. So to ask questions and then think about, how can I answer that question? What kind of data do I need to collect? How can I analyze that data? What does that data mean? So I don't know if you have noticed on the math standards, one of them was data analysis, statistics, and probability, which may sound like a lot to do with young children, but I absolutely assure you that children can engage in this process. They can ask questions, and then they can collect information. They can analyze that information, and they can think about what that information means. So what would happen if we put Mentos in the soda? How high do we think that the explosion might be? Does the explosion get bigger or change if we put more Mentos in? What kind of data could we collect? How could we analyze that data? So very important to engage children in this process. So just a little bit more on exactly what that inquiry process looks like. So When we are engaging in inquiry with young children, we want to allow them to go through this whole process. So it starts with noticing, wondering, and exploring, and asking a question, and then talking about what question and what do I think will happen. So if I do the thing that I think will help me to answer my question, what do I think will happen? It's very important to have that prediction so that children can start hypothesizing and thinking about what are the likely outcomes of their plan. So then they should go out and try it out. They should conduct that investigation. They should use those plans and see what happens. And then based on what happens, they have to come up with some sort of explanation, like why do I think that happened? Why do I think I got the result that I did? Why did I, if I got the result I was thinking that I would, why? If I didn't get the result that I was thinking I would, why not? So like putting the Mentos in the soda bottle, like, did it do what I think it was going to do when I put the Mentos in? If it didn't do that, why? Like what would be my explanation? And then also communicating those findings to other people, going and telling someone, I really wanted to see what would happen when I put this baking soda and vinegar together, and I thought this is what would happen, but instead this happened, and I think this is why it happened, and telling someone about that process. So not just children have a million questions, not just sweeping their questions under the rug, but teaching them how to take their questions and have actionable items. So what can you do with the questions that you have? So not just throwing questions out there in the universe, but how can we make those questions meaningful, and how can we get the answers that you want? And then how can we explain to other people what process we went through to try and answer the question that we had? That's the inquiry process, and super important for young children to be able to develop their science skills and to develop their skills of curiosity and learning. On this slide is general skills that we expect to see in preschoolers and early elementary school age children related to their ability to participate in the inquiry process. So this is not broken down by age because there really aren't milestones that are broken down by age in this area, but this will give you a general sense of what children are able to do and how they're able to participate in the scientific inquiry process. So all young children up through the age of 8 or 9 use exploration, so they need hands-on activities where they can explore and touch and do, and that is how they learn best, is through play and through hands-on child-driven activities. So that is the best place to navigate these kinds of inquiry skills. They are able to use observation and discuss common properties of objects, how objects are different from each other, to compare objects and materials. They can sort by different properties. So again, very young children are going to, if we go back to our math skills, they're going to support by maybe one dimension like color or shape. But as kids get older, they can sort and categorize by more dimensions and understand hierarchies in the things that they're categorizing. They can use simple tools like microscopes and tweezers and the tools of science that we would need to use to find out data and understand the world around us. So children can use those kinds of tools. They're able to record information through representational drawing. So even very young children can make simple graphs, like a simple bar graph about, what's everybody's favorite color. And then you make bar graphs representing that. They can also do simple pie charts, and as children get older, then they can do line graphs and other kinds of ways of recording data. Children can also draw the things that they're seeing, draw the things that they're noticing, and draw the results of their experiences. Once they get older, then they can write down things that they have learned and discovered. They can use their past experiences to think about what might happen. So that understanding of cause and effect that was being generated even when children were babies, understanding that if I do something, then something in turn will happen. allows them to be able to make predictions about what effects might come from different experiments and forays into trying to figure out how the world works. They also have better memory, so they can think about things that have happened in the past and how that might apply to things that they're currently doing or in the future. They understand relationships among objects and materials and things in the world. So when we were talking before about being able to comment on position kinds of language, so up, under, over, less than, more than, all that comes into play in noticing form and function of relationships. They can share their ideas and their observations in conversations, in talking with each other, in writing things down again when they get older, and they can work cooperatively, which is a great way to navigate investigating the world around you. So now that we've talked about what cognitive math and science skills consist of and what particular skills we expect children in the early childhood period to have, we'll spend the remaining slides of this lecture talking about how to best facilitate these kinds of developmental skills. So we'll start by talking about how to facilitate cognitive development, then how to facilitate math development, and then how to facilitate science development. So in terms of cognitive development, I mentioned on the previous slide that children learn best through hands-on exploration and through play. So we definitely need to make sure that we provide opportunities for children to engage in hands-on learning with play-based materials where they're having an opportunity to interact with adults and other children. That is the best way to learn all kinds of things, but particularly cognitive skills, science skills, and math skills. We want to make sure that we provide children with something called physical, social, and logico-mathematical experiences. So this is something that Piaget talked about. So physical experiences are things where you're learning about the properties of objects. So you don't even have to know the names of the objects, but you can put your hands on a table and feel that it's hard and it's smooth and it's heavy, and put your hand on a tennis ball and feel that it is round and that it is furry and it's hard to squeeze. You're learning about the objects in the world around you. And then social knowledge is when adults come give you vocabulary to go with those physical understandings that you're having. So that's a tennis ball. It bounces. It's hard. It has a furry outside and a rubbery middle inside, and then it's hollow in the very middle. A table is hard. It's made out of wood. So the social experience is giving the vocabulary. The logico-mathematical experience is allowing children to experience the differences among things. So to notice that a table is hard and a couch is soft, but they're both heavy. A chair you can sit on, but it's small, and a couch you can sit on, but it's bigger. So noticing relationships among objects and how objects sort of fit together and work in the world, that would be logico-mathematical experience. We also want to make sure that we allow children to have a variety of activities that get at all different kinds of cognitive skills and honestly math skills. So we want them to be able to match items in their environment. So when they're putting away the blocks, put the blocks away on a shelf that has labels that are the same shapes as the blocks, so you know where to match things. To have pattern blocks and make groups of things that are the same shapes and the same colors. To talk about objects in the world and how they are the same and how they are different. So we could even talk about children in the classroom and what things they have in common and what things they have are different. Cause and effect, so allowing children to try things out and then see what happens once they've tried it out, so they can see what kinds of effects they're having on the environment around them. Putting things in order of size, that is seriation, so lining children up from the tallest to the shortest to see sort of how kids line up. Also temporal ordering or time seriation, so what happens first, second, third, and fourth. Conservation, understanding things like if I pour water into a tall skinny glass, I did not get any more water. It just looks different in that tall skinny glass. Again, very Piagetian. So hopefully in other classes you're learning about those Piagetian conservation tasks where children learn to hold constant matter and volume and size and things like that. We also need to make sure that we ask open-ended questions, questions that encourage children to figure things out. So not just ask them questions that we already know the answer to, but ask them divergent questions where they have to think and come up with an answer and sort of think about and figure out what's going on in the world around them. So next we're going to talk about how to facilitate math. So it's really important to understand that young children actually do encounter math every day and that they actually understand a lot about math without us ever teaching it to them. But we need to take advantage of the fact that math is everywhere and children are interested in it and have some innate knowledge of it. So that is this first bullet about building on children's informal and intuitive math knowledge and their natural desire to learn and solve problems. So you'd be amazed at what children can do if you give them the opportunity. And there really is a lot of opportunity. So your chapter for this week talks about everyday mathematics. And basically what that is it's just math is kind of everywhere around us. And there's lots of instances where we can think about how much of something there is, how little of something there is. I have more of that than you do. We're going to the store to spend money. So really thinking about like all the ways math happens in our everyday lives and then including that in children's experiences. Your book also talks about mathematizing. So really when something math is happening in the world, like talk about it. Oh, I need to add that. I had a list, but I needed to add 2 more things. Now I have 32 items on my list. I'm going to split that in half. Then you'll have 50% and I'll have 50%. So really like being conscious of the fact that math is everywhere and really highlighting it and pointing it out and playing off of the interest that children have naturally in this topic. Making sure again that learning is active, that it's play-based, that children are exploring, that they're able to solve problems that are important to them by using math skills like what size shoe do you need? I don't know. Let's go measure. Let's figure out what we do to find out what kind of shoe size we need to get. Making sure that children are not just being taught directly by us. So we want to facilitate as adults, but not directly instruct, especially when children are younger. When children get older, we can do more direct instruction, but much of math, and I think this is unfortunate because by the time we start teaching math in school, we think we have to sit children down and directly instruct them, and we really don't. There's so much math that happens throughout every day that we can take advantage of. So I would encourage you to, think about how you can make things more active and hands-on, where you're just kind of helping children rather than sitting them down and forcing them to do a worksheet or forcing them to listen to a math lesson. Incorporating math everywhere in daily routines like snack and going to the restroom, all of the different areas of the classroom. So maybe you have a dramatic play area and it is a pizza shop and you need to have a cash register and you need to have some money to pay for the pizza and a menu with prices on it. But making it everywhere. There's a great article on this slide from 0 to 3 about making math language part of all the things that we do every day. Encouraging children to draw out what they see. So you can see in this little picture on the right, the child is being encouraged to make tally marks. So there's pictures of the coins, the child has real coins, and they can make tally marks to represent how much of each coin they have. So encouraging children to put down on paper in meaningful ways the things that they're noticing and taking in related to math. We need to model mathematical language, so we need to use math language ourselves, even though we're not necessarily that fond of math. We need to become fond of math because we need to be enthusiastic and we need to talk about math and make that part of our vocabulary. And then again, just integrating math anywhere that you can throughout the whole curriculum, in every center, in every aspect of the day as much as you can. So we have a few slides on how to facilitate science learning. So let's first talk about focusing on big ideas. So big ideas are like, why do things bounce? And why do things stick to each other? So not like little micro questions, but like the bigger things. So if they notice that a lizard can run up the wall, and they go, oh gosh, how can a lizard run up the wall? Why don't they fall off? And then you could segue that into, I don't know, let's learn about that. Like, how do all kinds of things stick? Like, how does a Post-it note stick onto something else? And how does the lizard stick onto the wall? So take those micro things that children are interested in and turn them into big ideas if you can. Help children to gather information. So if they want to know something, talk with them about, what do you think we could do to find this out? And then help them to go do that. Help them to use the tools, help them to get that social knowledge or that social experience so they have a vocabulary about what kinds of activities they're doing. Making sure that children get to do those process-oriented things. So we talked about that with art, but it's also important with science as well. Children should have the opportunity to solve problems that are meaningful to them, not just problems that are kind of in the abstract, but things that they really want to know about and they're really engaged in. So we've talked about encouraging representation. We've talked about asking open-ended questions. So that is the same here. We've talked about enjoying yourself. So not just enjoying yourself with math, but enjoying yourself with science. Children need to see us liking STEM. If they see us enjoying and liking STEM and wanting to do it on a regular basis, they like us and they want to do what we're doing. Go outside. Go look around at the world. Go bring materials in. Go find experts to come in and talk to the children. Like, as much as you can, like, go out and about in the world. When my kids were in elementary school, they learned about volcanoes in class, the different kinds of volcanoes, and it happened that summer that we went on a trip to national parks where different volcanoes were at, and they immediately learned more in that time because they could now pair what they were learning in class with what they were seeing in the real world with these volcanoes, and they still remember quite a bit about volcanoes even today as adults. And definitely go outside and incorporate nature. Most of science is outside. It's not all that much inside, so good to go out and about in the world. This slide is from your book and shows some other effective ways to help children be more proficient at science. So some of it is stuff that we've already talked about, but I just really wanted to highlight this table in your book. It's a good one for thinking about how to help children to activate their STEM interest and facilitate their STEM skills. So I did want to kind of end this how to facilitate section with talking about something called the spiral curriculum. And this is something that we can actually apply to all different kinds of curriculum things. So we can apply it to language and literacy and the arts and social studies and physical education, but oftentimes it gets talked about when we're thinking about cognitive development, math development, and science development. But just remember, it can be used for all different kinds of things. So there was a gentleman named Jerome Bruner. He was a theorist, and he had this idea that you should teach children in kind of a cyclical spiraling manner. So you start with, when you start with new content, it should be simple, and then you kind of work your way out. So we don't teach children to divide right from the beginning. First, we teach children to count and recognize numbers. Then we teach them about adding and subtracting, but not even with numbers and symbols. Then we work on adding and subtracting with numbers and symbols, and then we work our way up to multiplying and dividing. So we're spiraling out. We're starting very small, very narrow, and then every time we revisit a concept, we add more new content onto it until we get mastery. So you can see an example of what a spiral curriculum would look like and sort of what we should be paying attention to at different grades. So that is the graph on the bottom right of the slide. It shows that we should spend a lot of time on number at the beginning, and then we can spend less time on number after they master it. With algebra, we'll spend a little bit of time at the beginning because we've got to get those number skills going and solid, and then we'll spend more time on algebra later on. Geometry, we kind of stay around the same. Data analysis and probability, we stay kind of the same. We spend more time measuring at the beginning and then less time later after children get the hang of it. So we're adding on until there's mastery, and then we start kind of working out of focusing on a particular thing. But I would really encourage you, particularly with science and math, to think about how you can spiral up and out so that you're starting with small topics that are meaningful to the child, personally relevant to them, and then you're working your way out to concepts that are more difficult, complicated, and farther away from the child's day-to-day experience. And just one final note in this lecture. So we did talk about at the beginning that children of low income are less likely to have math and science opportunities. And so we know that there are gaps between lower income and higher income children. Your textbook this go around also talks about the fact that there are gaps for girls, that girls often have less access to math and may do more poorly. But another group we need to pay attention to is Black boys. So even though boys tend to have more math opportunities, Black boys don't seem to follow that rule. They seem to have fewer opportunities than girls and boys in general. Even if they are showing signs of being interested in math and good at math, they may still have fewer opportunities. There's a lot of educational things where Black boys are likely to not get the same opportunities as other children. So we really need to make sure that we're giving equal access to STEM opportunities and experiences so that we don't have those gaps later on down the line. And we also need to make sure that children have access to technology, because often math and science, when we're exploring math and science principles, technology is part of that package. And there is evidence to show that low-income children are less likely to have access to technology, which is partly why it's so important to have appropriate access. And we've talked about appropriate access in other lectures, but why it's so important to have appropriate access, the right kinds of technological tools so that everybody gets the chance to be up to speed with those skills and abilities.